Hello guys, so let's start with our class. So today we're gonna uh, start finding volumes. Last class we started. So let me go back a little bit for what we discussed last time. Okay. So uh, we gave an example of finding the volume of a bread, right? A piece of bread. So what we could do is take slides, right, and find the volume of each slide. So this one plus this one, and so on. So this will be the volume of xi. So this is 1, this is 2, this is 3, and so on. So you make the sum of all the slides, and then you'll have a good approximation of the. I mean, you'll find exactly the volume, right? But we will see that we can also do some approximations for examples like the one over here. So we can make approximations. We want to find a volume of something that we don't know exactly. We can make approximation of 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 this volume with a final approximation, similar to partial sums with area. Okay, but at the end, when we take the limit of these slides, when n goes to infinity, we will get exactly the volume. Okay, that's kind of, and then we will get this formula. So that's really what we're gonna use today. Okay, so that formula is what we're gonna use. So what is this saying? What is that formula saying? So it's saying that the volume of a 3D solid. So let me make this bigger. Whose cross-sectional x has area a of x, and with boundary points determined by x equals a, x equals b is given by this formula. So what is really saying is that you just need to make a slide. Let's say you slide this bread, right? Find this area, and then integrate between from the beginning to the end, and that's gonna be the volume. Okay, so let's make an example. So this you'll see how it works. And then here we have some steps. This is from the notes, by the way. These are the notes that are available since last week about this. So first we're gonna make an example, easy example. Let's see. So let me go back to my calculus new book. So we're gonna call this a volume, and they call it disc and washers. Okay, that's how they call it. Okay. So let's make our first example. So this is, this is gonna get a little bit messy or complicated, but you need to go back to the beginning. Okay, so when you got confused, go back to this example. So let me write example. So example. So find the volume of the solid obtained by rotating and we're going to do a lot of examples, okay, about the x-axis so let me see. Find the volume of the solid obtained by rotating about the x-axis. The region under the curve y equals a square root of x from 0 to 1. So, so basically we have square root of x looks something like this. Like that, okay? So I want it from 0 to 1. So let's say this is 0 and this is 1. So what you're going to do is rotate around the x-axis. So this is the x-axis, this is the y-axis. So when you rotate, you'll get something like this, okay? So you'll get this solid, okay? So now, that's the volume we need to find, okay? So what is the formula we have? So the formula we found, or we got is the volume of this is the integral between a and b from a of x dx, okay? So what is a of x? A of x is the area of one disk or one slide, okay? So what we need to do first is to make a cut, okay? So let's make a cut, like slice it, slide. So we will get something like this. So if we cut it over here, so you make a cut over here, you will get something like this. So right, and this is the cut, but the formula is saying we need to find this a of x. That's the area of the front face. So you don't worry about you don't worry about the back part. So you want to find the area of the face, okay? So for that we need to review something, right? But actually that's a circle, right? Because it's a totally perfect circle. So let me make it better because it looks like doesn't look like a perfect circle. It has to be it's a perfect circle because you are rotating around the x-axis. So that's why we can do this problem. Okay, it's a perfect circle. So we know a formula, right? What is the area of a circle? We have, let's put it here.
Pi r squared.
So we're gonna put here so I say this is x. So area of a circle. So you need to identify the radius. So the radius. So something important here, guys. So the radius could be this, could be this, could be this one, right? In all the cases, it's the same because it's a circle. It's a perfect circle. But since we wanna play smart, let's take this R. Okay. So let's take this R. So the area of the circle is pi R squared, correct? That you learned that in high school. Actually, we didn't prove it, but we could prove it. So probably we're gonna do one little, we're gonna do a little break one day, and we're gonna prove this, that the area of a circle is pi R squared. My next example is to prove the volume of a sphere, okay? So, because you learned that in high school, but you had no idea where it is coming from. So that's kind of the idea of this class, these calculus classes. You need to make sense of all those formulas you learned from high school. It has to make sense now. Where are these formulas coming from? It's not like a miracle that they show up, right? That's the advantage in physics or chemistry. In physics, you have some formulas and just, you know, some genius created with a lot of experiments, and that's it. That's the formula, and you just use it. You had no idea how it was created. At least you have a lab and you do the same experiment. But the formula is created. Here, you can create your own formulas all the time in mathematics. You create your formula. So we can prove that this the area of the circle is pi r squared, but you know that was for part of the exam 1, no exam 2. So I will do probably one of these days. But so that's the area, right? But we have some extra information. So we have that this function, this curve is y equal square root of x. So this is y. So this is the high, the high, the high, the high, the high. And this is the high. When I cut it at the point x, okay? So I made my cut on some x. This is my x, okay? So my high is square root of x. So this radius is y, okay? That's fundamental to understand the whole thing. So your radius, and most of the time is gonna be just y. I mean, we're gonna put, for this kind of exercise, it's easy to see that it's just y, okay? So this r is actually y, right? And that's why you can cut anywhere, because it doesn't matter what x you choose, the formula is the same, okay? So this y is, this r equals, radius is equals y, and y equals square root of x, right? Because that's my function, that's how high this it is, okay? And I could do the same experiment with any function. You could do s cubed, you could do x squared, you could do whatever. So the process will be the same, okay? So many possibilities to do same exercise here. Okay, so now that we know the area of the circle, so let's write what is this a of x then. So this a of x, so let's make a parenthesis here. So a of x is this, the area of this guy. And then you got pi r squared. But r is just y, so you got pi square root of y squared. Okay, so what you get is, oh, sorry, no, square root of y, sorry. Sorry, let me fix this. So r equals y, right? So y squared, but then this is pi, and then this is squared. Instead of y, I have a square root of x, because it's a function of x. I'm rotating around the x-axis. Since I'm rotating around the x-axis, it's going to be a function of x. So finally, what I get is that this is just pi of x. It's a of x. So all I had to do now is find my integral. So my integral is volume equals integral. So what is a and b? So they told us from the beginning, you are integrating from 0 to 1. So integrate from 0 to 1. And instead of a of x, I have pi of x. So I write pi of x dx. And then we got pi between 0 and 1 of x dx. Then you integrate. So you get pi. So what is the antiderivative of x? What is this?
X squared over 2.
X squared divided by 2 between 0 and 1. So finally we got just pi halves, right? Because when you plug it 1, 1 squared is 1 minus 0. So you see, the integral is piece of cake, okay? It takes us a little bit to make the draw, cut the slide or the disc. Really, the key part of this process is find the area. You need to find this a of x. And once you find that, you are done, okay? So let's make another one. And then this is going to be interesting because we know this one. We know the answer for this one. So let's use this formula. So example, we're gonna find the volume of a sphere. So let's say we have let's say we are in 3D and we have a sphere. Okay. So somebody remember if this is a sphere, what is the volume of a sphere? From high school. So what is the radius? If r is the radius, so this is the radius. What is the volume of a sphere? So it's not a circle, right? So
4/3 pi r cubed.
correct. So the volume of a sphere is 4/3. What else?
Pi r cubed.
Pi r cubed, correct. Thank you. So that's what we need to find. Okay. So let's follow here the directions of the node, of the nodes. So sketch the region that we will revolve and identify the axis. So sketch the solid and a typical cross section at x. The typical cross-section is extremely useful. So we need to make a cross-section. So when you make a cross-section, what do you get? So you cut it. That's, think on an orange. You cut it, and what do you get? When you cut an orange, you get basically a circle, right? And the little piece extra, like that. But we said, we just cut it, and we want to find is the area of the cross section of the front. So we want to find, that's our piece of orange, and what we want to find is this area. Okay. So there are a couple of ways to do it. So we need to think, how could we make, so based on the previous example, how can we make a sphere? So we can have the following. So we want a function on it. So I could take I could have a semicircle and rotate it around the x-axis, right? So if I rotate this semicircle around the x-axis, I'm gonna get a sphere, yes or no? So think you have a semicircle and you rotate around the x-axis. You'll obtain a sphere, yes or no?
Yes.
Yes, okay, thank you. So, so basically we are pretty much in the last example. That's what I did the last example first. Books usually do this one first. I like this one because this one is easier. So what do we do? So we know the circle, but fundamental, we need the y. So here they tell us the y. Y was a square root of x. Okay. So let's make the general case. Volume of a sphere of radius r. So to make a sphere of radius r, so it starts and ends on r and minus r and r, correct? So what is I need the function. So I need this function. Somebody remember what is the equation of that function? So we can start with what is the equation of a circle? So we had talked about that before here. Radius r. So what is the equation of this circle, guys? Everybody knows. We had used
Pi r squared.
Say again?
No. Pi r squared.
No, that's the area. I'm talking about the equation of the circle. Because I have the equation here. The equation for this example before was y equals the square root of x. And it was this guy over here. Okay, so now, and that's what I rotate around the x-axis. Now what I'm gonna rotate around the x-axis is this guy, the red one. So I need that equation. So what is the equation of the circle? Of this circle over here?
Y equals square root of x.
Say again. Y equals
The square root of x, or is that the wrong one?
No. But let me write the first one. So the equation of the circle is, oh, you know when I did this? I did this when I do the review in trigonometry. So it's x squared plus what? Yeah, well, x squared plus y squared. Yeah, somebody told me by the chat. X squared plus y squared equals r squared. Okay, this is r. Okay. But as in the example before, I need to have this equal, y equals to something. I need y equals to something. Because that's what I did in the last example. See, I have y equals square root of x, because it was this one. So I need to solve by y. So I'm gonna solve by y. So I'm gonna do y squared equals r squared minus x squared. Then take the square root both sides. I got y equals plus minus a square root of r squared minus x squared. So my question is, do I choose the positive or the negative?
Positive.
The positive. So for the equation of the circle, this is the positive is this one, r squared minus x squared. And the equation for the negative is this one. It'll be minus r squared minus x squared. So remember, it has to be a function. So I cannot put the whole thing because this is not a function. We'll hit twice. So I need a function. So so in order to do the revolution, I just need the top part or the bottom part. I could use either way. So I'm gonna use the top part. So in this problem was the y function was hidden. So that's basically what is hidden most of the times. So you need to find the y, the function. So this function is y equals a square root of r squared minus x squared. Okay, that was hidden, that was not given. In the previous example, that y was given, was square root of x. Okay, so I need to find it. But now I'm pretty much ready to solve this problem, because I do the same. So let me erase this so I can. So what I need to do, I need to know is the radius. I need to know the radius. So my radius is this guy from here to here. Of course, it's also this one, but uh-oh. It looks like I did something. Okay, so it's also this one, right? But that one I cannot find. This one I can find. From here to here, that's just y, right? It's my cross section on one point of on some x. So this is my volume, my sphere, and I'm here, and I step on some x, and I do my cross section. No, actually. Like that. So that's my cross section on x. So all that I need to do is find my integral, because this is y. Okay. And y is r squared minus x squared. So we follow the example before. So the area, or a of x, equals, in this case, is pi r squared, but r is just y, but y is a square root of r squared minus x squared. So that will be pi square root of r squared minus x squared. Okay. But now the square cancel with the square root. So I can do the following. I got a of x, a of x, a of x. Then I got pi r squared minus x squared. Okay? So that's my a of x. So following my formula, that is over here, volume equals integral between a and b of a of x dx. So we follow that formula. Volume equals integral of a of b of ax dx. And then we get integral of pi r squared minus x squared dx. Now, which one is a, which one is b? So you guys tell me which one is a, which one is b. What is a?
Negative R.
Negative r. And b?
R.
R. So this is negative r to r. So please find this integral. So it need to give you, as we said, 4/3 or 4/3 pi. What do we say? 4/3 pi r cubed. That's what you need to get. 4/3 pi r cubed. So let's do that. Let's do 4 minutes. Or maybe 3 minutes. So 3 minutes for you to find this integral. Go ahead. Okay, let's do it together then. So we take the, somebody got it? So we take the pi outside, then we get integral of minus r and r squared minus x squared dx. Then we get, then we integrate. So there'll be pi, and then what is the derivative of r squared?
R cubed over 3.
Just the r squared. So let's, the next one, what is the derivative of x squared? S cubed divided by 3, right? But r squared is a constant, right? So what is the derivative of a constant? So r is like 5 or 1. We're just doing a general formula, but it's really a constant. So what will be r squared x, okay? Like the antiderivative of 5. The antiderivative of 5 is 5x. What is the antiderivative of r? R is a constant. So the antiderivative of r is just rx, okay? Oh, same thing if it's r squared, so it's just a constant. So, and then we evaluate between minus r and r. So we get pi, and then evaluate at r, we got r cubed minus r cubed divided by 3 minus, then you got r cubed minus, and then this is minus r cubed times minus. So I think we'll get plus, right? So we could, well, let's do it slow. So it will be r cubed minus r cubed divided by 3. So it'll be r cubed minus r cubed divided by 3 minus r cubed. Oh, you see, good thing I did it slow, because r cubed times minus r, so that will be this minus r cubed over there. Because when I plug in the minus, so I'll get r squared times minus r, that will be minus r cubed, and minus r cubed divided by 3. So we'll see. So we got here pi, so r cubed minus r cubed divided by 3 is 2/3 r cubed. And then minus, and then we get minus r to the cube, that will be minus 10 minus, that will be a plus finally here. Let me put a plus here. So it will be r cubed minus, and minus r cubed is minus 2/3 of r cubed. So then minus 10 minus gives you a plus, so that will give you 4/3 pi 4/3 r cubed pi. And that's what we wanted to show. Okay. So that's the famous formula 1,000 years ago, but we can do it today with calculus. Okay. Okay, so that's one application. People have been using this for a long time. So let's do now an example. So this example is for you guys. So, I mean, in my regular class, if we were face to face, this would be a quiz. But right now I cannot make a quiz, but it's an assessment. So you need to be able to do this by yourself in order to continue, okay? Otherwise, it's not gonna be a very good idea to keep going because you're gonna get all confused. Let's see what example can we do here. Let's see if we have something in the notes we can use. So we did this one. This is just similar. It just radius is 2. Okay, so we did that example. So you see they got from -2 to 2. And this is the section. That's what is better that you take at least a look to the notes before class, because of course this is a much better graph than the ones I'm doing. Okay? This my radius is y, and that's what we're doing. Okay. So we solve this one. We also basically solve the same one. Square root of x. Now this one, but this is around y-axis. No, we need to wait before going to that one. I mean, it's very similar, but I wanna, yeah, that is not. There's they're pretty much ready doing the next case. So let's make our own. So same problem that the first one. Any function, we can do the same thing with any function. So you do enough problems of this, you will see that all these problems are basically very similar. Okay, so you just need to do a few. So let's do example. So same that example one. So the function we're gonna choose. Let's choose y equals x squared. So you're gonna find the volume if the function is y equals x squared, right? And you're gonna rotate it around the x-axis. So when you rotate around the x-axis, it's gonna look something like this, right? So find the volume between 0 and 1. 0 and 1. So same example that the first one. So find that volume. So let me give you 12 minutes. So to do it perfect, okay? So go ahead. Okay, so what answer do you guys get? So I saw somebody put pi over 5. That's correct. Well, let's go and do it. Okay. So let's see these notes and see if this makes sense for us or not. So we're gonna do all these steps over here. So sketch the region that we will revolve and identify the axis. So we did that. Sketch the solid and a typical cross section at X. The typical cross section is extremely useful. Yeah, we did that. Find a formula for AX, the area of a typical cross section. So we have to do that. Find the limits of integration. That will be easy because it's between 0 and 1. And that's hard to integrate. So really, we just need to go here. And so, as I said before, basically we need to find this area. This is the face. Okay. Any section, you make a section here, it's gonna look the same, right? So when you do the section, it's gonna be a circle. The important thing here is what is the radius of the circle, because it's all that it matters, right? Because since it's this graph is rotating around the x-axis in this case, so it's gonna be a perfect circle. So we need to find the r, the radius. So you can cut it. You can cut it here. You can cut it here. You can cut whatever you are. It doesn't matter because it's in terms of x. Okay, and that's why the radius is in terms of x. So whatever you cut, the radius is in terms of x. So it doesn't matter where you cut. So this is my radius. So what do you guys say? What is my radius? You guys are quiet today. What is my radius? So this part is this part over here. Okay. So my radius is just y. Okay, you see? This is my original function, y. So in this case, it's x squared. So all that I need to do is the volume of x is the integral between the values that in this case is 0 to 1 from a of x dx. But we know that a of x is this guy over here. So the area of this guy is area is pi r squared. So this area is pi. R is just y, so pi y squared. So that will be what? Pi x to the 4, right? So we put it right here. So that's my a of x. So I have to put it 0 to 1 pi x to the 4 dx. And that will be pi integral between 0 and 1 of x to the 4 dx. And that will be pi x to the 5 divided by 5 between 0 and 1. And then you will get pi divided by 5. Okay, so that's my volume. Okay. So now we can move on. So somebody's asking why radius equals y. So that's the whole point. That's what we have been doing all the class long. So remember, from example 1. So when you had seen all this, go back to your beginning. The whole point is that you have this is y equals a square root of x. So when you rotate it around, you see that immediately after you rotate, that becomes, this is your radius. So what is this? This is how high the function is at x. And who is determining this? This is y is determining this. So that's, in this case, y is the radius. This is the whole process. You got the function, you rotate it, and once you rotate it, that's why it becomes the radius equals to y, because you are rotating around the x-axis. So that's what is important. The whole explanation of the exercise and the example to understand why y equals r. So there are other formulas. We're gonna do tomorrow other formulas, and they are a little bit more straightforward. So there are some problems you can use this. I like to use this when it's rotating around the x-axis or the y-axis. Then there are others, and we will gonna do tomorrow. They are slightly different. So there is a formula for those, and they turns out to be easier because there is a very specific formula to solve it. Okay, so we'll do that tomorrow. But okay, so let's do the last example. I'm gonna rotate this example. We're gonna rotate around the y-axis. So, for example, so find the volume of a solid obtained by rotating the region bounded by y equals s cubed y equals 8 and x equals 0 about the y-axis. Okay, so let's see what is the meaning of this. So we rotate regions, okay? We rotate regions. So what is that? So we just graph it, okay? So is the region bounded by y equals s cubed? So s cubed is something like this, right? So then bounded by y equals s cubed, y equals a. So y equals a is something over here. This is y equals a. And then x equals 0. So x equals 0. So basically, is whatever is surrounded by the three curves. So we need to find this. We're going to get this region, and we're going to rotate it around the y-axis. We can erase. So we don't need the whole functions. So that's what we're gonna rotate around the y-axis. So that's what in the steps we said it's fundamental you make a drawing. So I think for this exam I can allow you to use calculators because there is all this setup. You need to understand the problem to be able to find to know what to integrate. So I think I'm gonna allow you to use calculators. So and you see the integrals are really easy. So so let's see. So we're gonna rotate around the y-axis. When you rotate that around the y-axis, you're gonna rotate it, right? So it's gonna look something like this. And you see, but look at this. This is right there. It's showing me the radius, right? So now when I rotate it around the y-axis, my formula changes. So when I was rotating around the x-axis, my formula was around x-axis, my formula was b of x equals integral ab a of x dx. Oh, no, actually not b of x. It's volume is a number, so it's not a function. This is just volume, will be a number. So now around y-axis, we get volume, and then there'll be the integral between, let's say, c and d of a of y dy. So it's basically the same argument, but instead of x, we are rotating around the y-axis. So we don't have to do the whole analysis again. Okay, so now we're gonna use this function. So this function over here, it says y equals s cubed. But I need my formula in terms of y, right? So I need to find f of y. So f of y, so in this case, I'm gonna change my axis. So this is a of y is gonna be, it has to be the area, right? So you make the slide, so you make the cut. This time the cut is horizontal, not vertical. So you're gonna cut it horizontally, like something like this. So when you cut it horizontally, your slide looks like, let me put it here somewhere. Your slide, when you cut it, your slide is gonna look like this, right? So again, this is the area I need. But look at this has. So when I put it over here, so I need to, let's put this red line again. So this, I cut that. So this red line over here is this red line over here, right? So now, but I forget a little bit of this of the. I need to see the face very good. So let's put the face. The face is gonna be something like this, and okay. So this guy is this guy. This guy is this guy, and this is the radius. That's my radius. So in this case, my radius, since it's given this, I'm rotating around the y-axis, it needs to be in terms of x. So in this case, my radius equals x. Okay, so you see this is y coordinate, x coordinate. So my radius equals x. So I need to solve here, instead of writing y equals x cubed, I will get, taking the cube root both sides, I'll get cube root of y equals x. This is my radius. So the first time you see this, kind of confusing, but we already did one example of this changing of for the area between curves. This changing of coordinates is very important in physics, in engineering, because it allows you to solve some problems easier. Okay, so now that we know our radius, so we can find our formula. So a of y is pi r squared, but r is x, so pi x squared, in this case is pi, and then a square, and I get the cube root of y. Okay, so this is, then I get a pi y to the 2/3. Okay, so that's my a of y. So I just need to use this formula. So my volume is the integral of pi y 2/3 dy, okay, because I'm rotating around the y-axis. So I take my pi, and then, where is y moving? Y is going, what are my y's? These are my y's. So y is moving from 0 to 8. Okay, so I integrate it between 0 to y. So you have to take calculus 3. This is going to be really useful for you, because this is what you're going to do all the time in calculus 3, 0 to 8. You have to change all the time coordinates. So then you go pi integral between 0 and a of y 2/3 dy. And then you get pi. So y 2/3 plus 1. So we integrate this, right? So this is y 2/3 plus 1 is y 5/3, right? Times 3/5. And you integrate between 0 and 8. So when you plug in, you get volume. So let me see. I can give you. You get 3/5 a to the 5/3 times pi minus 0. So y of 0 is 0. So I don't need to plug in that one. And that's gonna give you 96/5 pi. I'm following my notes, right? We don't have time to calculate it. But that will be your final answer. Okay. So now tomorrow I'm gonna teach you another method that is gonna help you to see when do you use this method or the other method. You can choose. But I'm gonna open the homework so you can start practicing. Okay. So I think it's 3:16. So I think we have enough material. So you can also go take a look to the notes. And these problems are slightly different than the ones I solved. Okay, so I do it on purpose. So you guys go there and try to solve the problem. Well, maybe this one is the same. You try to solve the problems by your own to see, and you compare. Oh, this is also the same. Yeah, sorry. So these two examples are basically the same. This one we will solve tomorrow. Okay, this example needs some explanation, but I will explain it and then I will teach you the new method that will allow you to solve also this method by the other method. And then that's pretty much it. Okay. So I'm gonna open the homework, so please start working. And then if you go to the announcements, I listed several problems. No, several problems, no. There are, you wanna see more videos. These people do a good job. In Khan Academy, they had this application of integral. So just keep the first one, average value function. We're not doing that. Motion problems, we are not doing that. No motion applications. We are going to do some applications, but in differential equations. So this is area between curves. You can go and see more video series between curves. We're going to do one tomorrow with sines and cosines. Then you have volumes. That's what we're doing. Cross sections. That's what we're doing right now. Cross sections. Okay. So you can see this. And Dick's method. This is also what we're doing. And we're going to do tomorrow washer method. Okay. So you see, you have a lot of videos, so you can do more practice if you want. Because yeah, this part is important to do nice graphs, and so it's important to have the geometric intuition to do this. Okay. So you can go and see all these videos. They're short. Okay, guys. So I'll let you go. So, oh, quiz. Yeah, we're gonna have quiz, but it's gonna due Monday. I'm gonna give you some time to catch up because after the exam, people finish a little busy. So I give you time, and it's gonna due Monday. So I give you time to catch up. But probably at the end of this week, we will be ready. We are done with the material for the second exam. Okay. So we'll see, but I think we are pretty much ready for the second exam at the end of the next week. Okay. So, and then that will be the end of integrals, and we will start doing something new, like call series and sequences, so something new. Okay. Okay, guys, I'll let you go.
Sir, do you need office hours today?
Yes, at 4:30.
Okay.
Okay.
Thank you, sir. Have a good day.
Okay, bye.